Okay, so I'm going to discuss first some prerequisites for linear algebra. What are the key things that we need to know in the topic called linear algebra? So first of all, we must be aware of what is the meaning of V over F is a vector space. There are basically 10 properties required for something to be a vector space, but in nutshell, you have to remember two things. Number one, if you take two elements V1 and V2 from V, then it implies that V1 plus V2 also comes from V. That means sum of two elements of V is also an element of V. The second thing is, if you take a V coming from V and alpha coming from F, then it implies that alpha V is going to also come from V. That means scalar multiple of a vector is also a vector. So if you take two elements from V and add them up, then the answer is again in V. If you take one element from V and one from F, then the product, which is known as the scalar multiple, is also going to be in V. So this is the key definition of what a vector space is. Though it has 10 properties, but these are the two key highlights of the properties, okay? The second concept that you must know is that of spanning. Now, what is the meaning of spanning? It comes from a word called linear combination, which is just an extension of the previous two properties that we have highlighted. How? So, suppose I have V1, V2, dot, dot, dot till Vn, and I consider a quantity called alpha 1 V1 plus alpha 2 V2 plus dot, dot, dot till alpha n Vn. Then this is known as a linear combination of VIs. And by the above two properties, see, alpha 1 V1 is going to be an element in V, alpha 2 V2 is also going to be an element in V, alpha n Vn is also an element of V, and because all of them are elements of V, their sum will also be an element of V. So we get that this entire expression that we have written, which is technically called as a linear combination of V1, V2 till Vn, is also going to be an element of V. This is the meaning of linear combination. When I say this set spans V, I'm basically saying that every element of V is a linear combination of V1, V2 till Vn. That means we write it like span of V1, V2 till Vn is equal to V. And what this means is that if you pick up any one arbitrary element from V, then we can successfully write it as a combination of VIs. So each and every element coming from V, that means for each x coming from V, there exists scalars alpha 1, alpha 2, dot, dot, dot till alpha n, such that when I say scalars, they are obviously coming from F, such that x can be written as alpha 1 V1 plus alpha 2 V2 plus dot, dot, dot till alpha n Vn. Of course, if there is a y that is required, then y will be some other linear combination. So it will be beta 1 V1 plus beta 2 V2 plus dot, dot, dot till beta n Vn. That is the concept of a set spanning a vector space. That means it covers the entire vector space, which means every arbitrary element is a linear combination of these VIs. The third concept that I would like to write on the board is that of linear independence. All these concepts are done in detail in the classes, but we are doing it like a recap so that I can do the theorem today by doing all these reviews nicely. So linear independence, we say a set V1, V2, Vn is linearly independent if and only if whenever alpha 1 V1 plus dot, dot, dot till alpha n Vn comes out to be 0. Any linear combination of these vectors equal to 0 implies that all the scalars in picture are going to come out to be equal to 0. So a linear combination equal to 0 has to imply that all the scalars in picture are 0. Then we say that VIs are linearly independent. The linear combination equal to 0 implies all the scalars are 0. Clear? The fourth concept required for today's theorem is that of FDVS. The full form of this is finite dimensional vector space. By the word dimension, we mean the number of elements in a basis. By the way, a vector space can have many bases, but what is unique about them is how many elements does it have. The number of elements in the basis is always unique, which is referred to as dimension of the vector space. And we are particularly interested in finite dimensional vector spaces. We refer to the dimension as dim V. So when I say dim of V is n, I mean that there exists a basis, say beta of V with n elements. That is what I mean. Okay. Also, when you have a linearly independent set, every linearly independent set can be extended to a basis. Why is that? Because there's independence already, covering has not happened, so you can add more elements as per the requirement so that the set that you get is now able to cover the entire vector space. Okay, so every linearly independent set can be extended to a basis. Like I said, each one of these concepts and properties have to be done in detail, but this in nutshell are the reviews that are required. The last review required for today's theorem is what is the concept of V by W. This is known as the quotient space or the factor space, and this is basically nothing but a collection of all cosets of W in V, which means that V by W is a collection of all elements of the form X plus W, where X comes from V. So this is a coset. X plus W is called a coset. Collection of all cosets is referred to as V by W. V by W, as you can see the word space being used here, which cannot be used lightly, which means that V by W is not just a collection. In fact, we can easily show that this is a vector space. Again, to come back to the first point that I had made, if something is a vector space, there must be two operations that you must be very clear about. One is addition. So we must know X plus W is added to Y plus W. How? It becomes X plus Y plus W. So addition of cosets has to be very clear. X plus W added to Y plus W should give you X plus Y plus W. And alpha times X plus W gives you alpha X plus W. That is how scalar multiplication of cosets is defined. Okay. Now, these are basically the 6 reviews that are required to understand the theorem we are going to cover today. So you must be clear about what is the definition of a vector space, what is the meaning of spanning, what is the meaning of independence, what is the meaning of finite dimensional vector spaces, what are independent sets and how are they related to the basis, and what in turn is quotient space. Now let's pay attention to the theorem that we want to do today. So the theorem that I'm trying to prove today is that dimension of V by W will be equal to dimension of V minus dimension of W. What in hindsight it's also trying to tell us is that if V is finite dimensional vector space, we know W is also finite dimensional vector space. We know that for a fact, and the difference of these two comes out to be dimension means we are also saying that if V is a finite dimensional vector space, then V by W is also a finite dimensional vector space. We are trying to prove the theorem that if vector space is finite dimensional, then its quotient space will also be finite dimensional. So, now this is a long theorem, something that students generally struggle with because they're not clear about the approach to this particular theorem or any theorem in general. So, every theorem has some components. First of all, you must try to write the things in steps. And what are the steps categorized as? You must know what is the beginning, what is the middle body of the theorem, and how the conclusion is going to be achieved. So for this theorem, you have to remember that in step 1, first of all, we introduce their dimension. So let dimension of V be n and let dimension of W be k. Obviously, k is less than equal to n. In fact, if W is a proper subset, if W is properly contained in V, then k will be strictly less than n. Then k will be strictly less than n. Okay, having said that, if you have introduced both the dimensions, that means you have introduced both the bases also in the picture, but we don't want the bases to be not connected with each other. We want them to have a connection with each other. How is the connection going to be established? Remember the golden rule. Always start with the bases of the smaller set in the picture. Out of V and W, W is a smaller one. Start with the basis of that. So let beta, which is V1, V2, dot, dot, dot till Vk, be a basis of W. If it is a basis of W, it is a linearly independent set. And by the review that we just discussed, every linearly independent set can be extended to a basis of V. So kindly extend this basis to a basis of V. What does that mean? We get a basis called, say, beta dash. Extension means it must incorporate all the elements that have already been introduced and more elements get added. So there is a Vk plus 1 dot 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 till Vn. Why till n? Because we already introduced the dimension. So beta dash has n elements. They have the first k elements that are coming from beta and the extra elements that have been incorporated. This is a basis of V. Now, first of all, at this stage, I would like to highlight that our to show is dimension of V by W should come out to be n minus k. That means we need to explicitly find a set with n minus k elements, which we think will form a basis of V by W. So, first target is to locate where the n minus k elements will come from. If you can see carefully, this is from V1 to Vn. So, these are n elements in picture. And these are k elements in picture. So if you have n elements and from there you remove the k elements, you are going to be left with n minus k elements. So these n minus k elements are going to be the elements that we focus on. So just consider the elements that were added. These are n minus k numbers. So consider Vk plus 1, Vk plus 2, dot 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 till Vn. These are clearly n minus k elements in picture. However, they are not n minus k elements of V by W because V by W, as we discussed in the review, needs to be the collection of all cosets. So what you're going to do is consider the cosets that can be formed with the help of these elements. So consider Vk plus 1 plus W. Remember, x plus W is a kind of elements that have that belong to V by W. So Vk plus 1 plus W, Vk plus 2 plus W, dot 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 till Vn plus W. How many elements are these? These are also n minus k elements. What is the advantage of these elements over these elements? These are n minus k elements of V by W. And we have reached a very important point because we have now constructed or considered n minus k elements of V by W. And we assert, so this is where we assert that these elements form a basis of V by W. So the first and major step that was being done is over here, and this is where we begin our step 2 with. So let's have a quick recap of what was step 1. Step 1, we have not done anything major. We have introduced the dimensions as some numbers. Let dimension of V be n, dimension of W be k. And we have to start with the basis of the smaller set. So start with V1, V2 till Vk, which is the basis of W. Extend it to a basis of V. The difference is the n minus k elements. From those n minus k elements, you create n minus k elements of V by W. And then you assert that this constitutes a basis. If you come to step 2 now, we assert that this set is forming a basis. You know, this step can also be bifurcated into 2. Because as discussed before, something is called a basis if and only if it is linearly independent and spanning. So we discussed linear independence separately and spanning separately. When I say something is a basis, it needs to be linearly independent as well as spanning. So what are the two things we'll have to show here? We assert they are linearly independent, and then we'll have to show that they also span V by W. Okay, so linear independence can be done only in one way, which is let a linear combination of them be equal to 0. So let alpha k plus 1 vk plus 1 plus w plus dot 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 till alpha n. Now let's just do this later because I need space, so I'll write this again. Alpha n vn plus w be equal to 0. Right? Now the review of how scalar multiplication is done for cosets. So this will be alpha k plus 1 vk plus 1 plus w plus dot 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 till alpha n vn plus w equal to 0. Now also a very important thing here, and I hope when you are looking at the structure of V by W, you know that this is the 0 of V by W. The 0 of V by W is actually, so please note as an extra review that 0 of V by W is 0 plus W, which is just W. So the 0 is not the number 0, it is actually 0 plus W. And so this is, say, review number 7 or something. And another review is how does A plus W become equal to W. The proof of this has been done earlier in the class. A plus W is equal to W if and only if A belongs to W. Keep review number 7 and 8 also in your memory when you're trying to do this. So when you open this up, sorry, this one will be alpha n vn plus w. So when you simplify it, it will become alpha k plus 1 vk plus 1 plus dot 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 till alpha n vn, this whole term plus w equal to w. Apply review number 8, you get alpha k plus 1 vk plus 1 plus dot 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 till alpha n vn has to belong to w. This comes from review number 8, which is when does A plus W become W if and only if A becomes equal to W. So having said that, this long looking expression is an element of W. The advantage W has is that its basis is already present. If you have a basis in picture, every element is going to be a linear combination of these elements. So alpha k plus 1 vk plus 1 plus dot 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 till alpha n vn can be written as beta 1 v1 plus dot 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 till beta k vk. Why is that? Because the v1 v2 dot 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 till vk was constituting a basis of W. So this expression is equal to this particular expression, right? And what does this give you now? We are towards the end of this, because now I can write this expression as beta 1 v1 plus dot 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 till beta k vk minus alpha k plus 1 vk plus 1 minus alpha n vn equal to 0, and vi's constitute is a basis of V. Therefore, they are linearly independent. Linear independence means whenever a linear combination is equal to 0, it will imply that all the scalars in picture are equal to 0. In retrospect, when we see, we only wanted these scalars to be 0 because we had taken the linear combination with alpha k plus 1, alpha k plus 2 till alpha n. So our aim was to try to show that they are 0 and they are coming out to be successfully 0. Hence, vk plus 1 plus w dot 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 till vn plus w is linearly independent, which was 50% of the work that was required to be done to show that this is going to be a basis. I hope it's clear. You've shown that it's a basis. So step number 1 was getting the n minus k elements. Step number 2, 50% of it was trying to show linear independence. Now coming to the grand finale of this question, which is the last step, which is now to show vk plus 1 plus w plus dot comma dot 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 till alpha vn plus w spans V by W. This has to cover V by W. What is the meaning of spanning? We discussed it in the review that every arbitrary element of V by W, we should be able to write it as a combination of these elements. Now, so for that we begin with let X plus W belonging to V by W be an arbitrary element. And we have to show that this arbitrary element can be written as a linear combination of these. So when I say X plus W comes from V by W, where does X come from? It comes from V. If it comes from V, therefore this X can be written as a linear combination of bases of V. So it is alpha 1 V1 plus dot 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 till alpha n Vn. Therefore, X plus W is equal to alpha 1 V1 plus dot 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 till alpha n Vn plus W. Remember, the golden rule of understanding every expression is knowing how it goes from LHS to RHS and also how it goes vice versa. What I mean, I will highlight here. When I was discussing how two cosets are added here, when we said X plus W plus Y plus W is X plus Y plus W, this is fine, but you must also know the reverse. So if you come across this expression, you must know how to split it up. Similarly, when you come across this expression, you must know that you can take the alpha common from here. This is where students generally struggle with, because they think there is no alpha here. The idea is not to take alpha common here, it is how scalar multiplication was defined. So if alpha times X plus W is alpha X plus W, then alpha X plus W, if you come across, the alpha can be written common. Having said that, this expression therefore can be split up as alpha 1 V1 plus W plus alpha 2 V2 plus W plus dot 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 till the last term will be alpha n Vn plus W, like that. Okay, this further is alpha 1 V1 plus W plus alpha 2 V2 plus W plus dot 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 till alpha n Vn plus W. There is an influx of more terms than we would require in our answer, because I wanted my summation to begin from k plus 1 go till n. I have till n, there is a k plus 1, but I don't want the first a few terms. How do I get rid of the first a few terms? By making sure that you remember that V1, V2 till Vk was a basis of W. So, V1 plus W becomes equal to just W by the review that we just discussed. Something plus W is equal to W itself if V1 comes from W. So, since V1 comes from W as it's a basis, this term just becomes the zero element. Similarly, this element becomes the zero element, and till k elements, they all become zero. The zero element of V by W. And the definition of zero element is when it is added to every element, it gives you the same element back. Therefore, so I would just write that down. Therefore, Vi plus W will just become W for all I going from 1, 2 till k. And hence, this expression just boils down to alpha k, and also W added to A plus W is just A plus W, because this is a zero element. Zero element when added to anything gives you the same thing back. So this boils down to just alpha k plus 1 Vk plus 1 plus W plus dot 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 till alpha n Vn plus W, like that. Right? This clearly shows that every arbitrary element has been successfully written as a linear combination of the elements that we were asserting constitute a basis. And hence we are able to establish, together with the linear independence that was shown earlier, that this constitutes a basis. So what have we successfully shown? We have been able to show that dimension of the quotient space is nothing but the difference of their dimensions. Dimension of V by W is nothing but dimension of V minus dimension of W. In the exam, either a theorem will come for about 15 marks, if not 20. Or an application of this theorem can come. So it's important to do theorems from two perspectives. Number one, theorem itself coming in the exam. Number two, a question coming on the basis of the theorem. So I'll give you a hint of what kind of a question can come. Show that dimension of, say, P2R, that is P2x upon P4x is nothing but, so dimension of, I hope you're clear about the definition of P2x. It is set of all polynomials up to degree 2. We have also discussed in detail why it has to be up to. So I hope you remember dimension of P2x has to come out to be 3. It is polynomials of the form a0 plus a1x plus a2x square. And so there is a 1x and a x square that constitutes a basis of this. Similarly, P4x also has dimension 5. So this will be equal to 5 minus 3, which is equal to 2. If this is a 15 marker, show that dimension of P2x upon P4x is 2. Obviously, you can either do this entire theorem and do this as a corollary, or you can write the direct solution of this by starting with the dimension of, sorry, this one would be the reverse. You have to write V and then W. So the P2x is going to be smaller and P4x is going to come in the numerator because this is a vector space, this is a subspace. The right hand side is fine. This is 5 minus 3 equal to 2. So it's P4x upon P2x because P2x is contained in P4x. So what I was saying is either you can write down the theorem and then do this as a corollary, or you can now replicate the proof that we did now but with regards to P2x and P4x. That means start with the basis of P2x. So the basis of P2x that you should consider is the standard basis 1x x square. Extend it to a basis of P4x. How do we extend it? 1x x square, x cube and then x4. These are the extra terms that have been added. You take these elements and make cosets out of them. So consider x cube plus P2x and x4 plus P2x. And then you assert that this set constitutes a basis of P4x upon P2x. So show linear independence and show spanning, which will be identical to the steps that we have followed in the theorem. So I hope it's clear. Please do the theorem and do this as an extra practice. Do it in both ways. Do it as a direct corollary. Also try to write down the proof of this so that it helps you to remember the steps that you followed in the main theorem first. Okay.